Yes.
Okay. Okay, so today we will be having a look at the mathematical structure and properties of graphs. So, from the previous lecture, does anyone remember what a graph is? Can anyone just explain what a graph is using only English terms? Okay, yeah, just
Collection of nodes connected by some paths.
yeah, connected by some, we call them edges. Okay, so there are some nodes, and there are some edges connecting to two nodes. Connecting two nodes. So each edge connects two nodes. For example, this particular edge connects node 0 and node 5. Okay, so does anyone remember how we represent a graph in a computer or like in any computational model? There were two ways of
Using
representing.
adjacency list and adjacency matrix.
Yeah, so adjacency list. So these are the two ways of storing this information about this graph in a computer. But what mathematicians tend to do is they talk about this mathematical object in a separate way. They define a graph to be something of the form G, P, comma E, where G is the graph, P is the vertex set, and E is the edge set. So you can think of V as V1, V2, N, graph with N nodes, and then E as a set of uh, pairs of these nodes. So this can be V1, V3, V2, V3, etc. V4, V5. Okay, that's all. In particular, E is a subset of V square. For undirected graphs, you can maybe assume that if V1 and V3 is V1 comma V3 is present, then there is an edge from V1 and V3, and then you no longer need V3 comma V1 to be present in this edge. But in directed graphs, you need like both of these carry different meanings. So in directed graph, V1 comma V2 uh, does not necessarily imply the same thing as V2 comma V1, because you can maybe define the first one to be from V1 to V2 and the second one to be from V2 to V1. So the important point here is that before we define this graph as a set of vertices and an edge set, we need to talk about its directedness, whether it's a directed graph or an undirected. So uh, for now, we will assume that whenever we talk about a graph without specifying with if it's directed or it's undirected, we assume that it's just an undirected graph. So over here, let's write this particular statement over here. Okay. Now, for example, in this graph, we can represent it in some way like v equal to 0, 1, 2, 3, 4, 5, 6, and e equal to, and there will be a lot of edges 0, 5, 0, 4, and so on. 4, 5, 1, 4. Let's not waste time by writing all the edges, but mathematicians write the graph in this format. Okay, so now moving on to the next topic that we will be discussing. We'll be talking about degrees. So, in the last class, the definition of degree was explained. So, does anyone remember the definition of degree for an undirected graph? degree of, let's say, vertex U. Let's write it subscript degree of U. Let's write it in the form d suffix subscript U. Does anyone remember?
The number of edges connected to a vertices.
Yeah. So the
Vertex.
number of edges connected to U, right? So for example, the degree of this will be 3 because there are 3 vertices, 3 edges connected to D0. I think clear till now. I hope so. Okay. So in undirected graphs, we have this notion of degree of a vertex. But in directed graphs, we have two separate notions. One is called the out degree, and another is called the in degree. So anyone anyone remembers the definition of out degree? Let's call it out of U.
Number of edges leading out of U.
It is leaving out of U. And similarly, this is number of edges incident on U. So for example, the in degree of 5 is 0 because there are 3 edges. In degree of 5 is 3 because there are 3 edges incident on 5. And the out degree of 5 is 0 because there are no edges leaving out of 5. For 4, there is only one edge leaving out of 4. So the in degree, the out degree of 4 would be 1. And there are 2 separate edges that are incident on this vertex 4. So the in degree will be 2. And so on. You can calculate the in degrees and out degrees for other vertices as well. Okay. So all of these were done in the last class itself. Now let's talk about some results that are related to degrees of the vertices. Okay. So the first theorem is also called the handshaking theorem. It just says that the sum of degrees of the vertices of an undirected graph is twice the number of edges. So this is also a pretty well-known fact, and this was also covered in the last class. So can anyone just give me a quick short proof of this fact?
Every edge is correct. Every edge is counted for 2 nodes.
Exactly. Every edge is counted for 2 nodes. So this edge is counted one for this and once for this. This edge is counted once for this and once for this. So whenever you insert one edge, your sum of degrees increases by 2. So does anyone know why this is called the handshaking theorem? Why does this have such a weird name? Okay, so basically the actual statement says that if there is a party of, let's say, n people and there are some handshakes that take place, then if you ask everyone how many handshakes were they a part of, and then you sum them all up, you will get that number to be equal to twice the number of handshakes, right? Okay, that's not a very relevant detail to what we are discussing, but anyway. So one corollary to this thing is that uh, number of. So first of all, let's define odd vertices and even vertices. Odd vertices are the vertices such that du is odd, and even vertices are the ones where du is even. Now, one corollary of this handshaking theorem is the fact that the number of odd vertices, so in E, such that du is odd. What can you tell about this number? The number of vertices such that the degree is odd. Okay. So this number has to be even. Right. Because if this number is odd, then sum over du will be odd because the number of odd vertices is odd. So the sum of degrees of all the odd vertices is an odd number, and the rest vertices which are even vertices will only contribute an even amount, so the net amount remains even. But you know that this total sum must be an even number, right? So the number of odd vertices has to be odd. So is this corollary clear, more or less? Over here, if you see, so I've written down the degrees of these vertices. So you can see that this is an odd vertex, this is an odd vertex, this is an odd vertex, this is an odd vertex. So there are 4 odd vertices. You cannot construct a graph such that it has only 3 odd vertices, right? Does that make sense? Or is there some problem with it?
Clear.
We will just briefly mention the analogous theorem to the Henging theorem for a directed graph. So for a directed graph, the sum of out degree is equal to the sum of in degree is equal to the number of edges. This is also pretty obvious because for every edge, in degree of one vertex is increased by 1 and out degree of one vertex is increased by 1. Right. So I hope this part is clear. Okay. This also means that so everyone remembers the depth first search algorithm that was covered in the last class.
Yes.
Okay, so what do we do in the depth first search? We choose a vertex, we see all its neighbors, and then we do depth first search on all of them with some memory of whether this vertex was visited or not. So basically, the time complexity of depth first search will be order n plus summation of du for all n, right? So for each node, you are going for all its neighbors for a further depth first search. Maybe you are returning back because this particular vertex may have been visited in a previous search, but nevertheless, you have to either check if this is visited or you have to go and visit this vertex and then further carry on depth first search. So one might argue that, well, the degree of a particular vertex may be as large as n minus 1, and since we are summing up that for all n, this should be order n squared, right? Is this true? Well, this is true if you are using depth first search for using adjacency matrices. Otherwise, what happens is in adjacency lists, this value actually becomes equal to, so this value is of order, this value is equal to twice e, right? So let's say size of e is equal to 1 m, then this value is equal to 2m, which is order n plus m. Now, in most of the competitive programming problems, what you're given is n comma m is less than 10 to the power 6 or 10 to the 5. Anyway, that means that this time complexity is sufficient for us to pass the time limit. Okay, so was there any doubt in this discussion? Let's move on. Now let's talk about another theorem. This theorem does not directly relate to the competitive programming aspect of graph theory, but this example actually gives us a this theorem basically gives us an example of a case where we can actually reduce a word problem that is in plain English to a graph theory problem. So this theorem says that if there are six friends, six people, then there is a set of three mutual strangers or three mutual friends. Okay. So for example, let's see what the attendee count is right now. Okay, so the attendee count is exactly six. So out of so all six of the attendees present over here, either one of these must be true. That uh, three of you must know all three of you, but so either one of them must be true. Three of you must know all three of you, or three of you must know none of the other. So you can find at least one such subset of three. Is the statement clear? So formally, if you have people numbered from 1 to 6, then you can find a subset of this number such that this is 3. Let's say S is equal to B1, B2, B3. Then it is either the case that B1, B2, B1 and B2 are friends, B2 and B3 are friends, B3 and B1 are also friends. Or it must be the case that B1, these two are meeting themselves for the first time, these two are meeting themselves for the first time, and these two are meeting themselves for the first time. Okay. So how do we prove this? So any idea how to make this a graph theory, how to model this as a graph theory problem? Okay. So what you can do is consider these six people as six separate nodes.
Do we use directed graph here?
Okay, okay. How do we use directed graph?
No, I'm just asking. I don't know.
Uh, no, actually, here there is one slight assumption that if A is a friend of B, then B is also a friend of A. Yeah. So that means that whether if you're drawing an edge between A and B, which I will be doing, if A and B are friends, then there is no sense of putting in directions for those edges, right? So if A and B are friends, then B must also be a friend of A. Then yeah, so there is no sense of direction that the friendship goes from A to B, right? Does that more or less make sense?
Yes.
Okay. Okay, now so for these six people, let's draw a graph such that every two people are connected by some edge. But let's draw the graph edges by different colors. Let's say we draw an edge by a pink color if they are friends. Okay, this means friends. And let's draw an edge by blue color if they are strangers. So in total, how many edges will be there? No one? There should be exactly six to two edges, right? Because for every pair you will have one edge. Okay. So now this particular model gives us a representation of the setting we had. Now what we have is a completely well understood mathematical model, and now we can argue stuff in this model. So how do we argue stuff? Well, we can maybe for this example we choose one particular node and observe that there will be at least 3 edges going out such that they have the same color. Why? Because, well, if there are 2 edges of pink color and if there are 2 edges of blue color, then you will have 4 edges, but you have 5 edges, so there must be at least 3 edges of the same color, right? Now let's call this vertex as V0, and the 3 edges that are of the same color, let them end at V1, V2, and V3. Okay. Now what happens is we observe these 3 nodes, these 3 edges. Let's yellow. This edge, and this edge. Now observe that if any one of those edges, so over here, if this is the edge we're talking about, if one of these edges are the same color as the edges V0, V1, or V1, V2, V3, V0, V3. So if one of those edges are of the same color as we have chosen, then you will get a complete triangle V0, V2, V3. This triangle will have all edges of the same color. That means they are all mutual friends or all mutual strangers, right? But what if there are no edges of the same color? What if this edge was also of the different color? Well, that means all these 3 edges are of color that are different from the edges joining V0 to V1, V2, V3. Well, since there are only 2 possible colors, these 3 edges must be of the same color. Then you can choose this subset V2, V3 such that V1, V2, V2, V3, V3, V1 are either all friends or all strangers. And that's it. That completes the proof. So, is this proof clear? I mean, the proof is not that important. The main point that we need to take away from this proof is that how to convert a problem that is given in plain English to a graph theoretic problem. So, is this proof clear, or there are some confusions regarding this? Okay.
Can you summarize once?
Okay. Okay, so I'll write it down. Choose any vertex V1, any vertex V0. Choose V1, V2, V3. None of them equal to V0, such that V1, V0, V2, V0, and V3, V0 are of the same color. This is always possible because if there are 2 less than or equal to 2 vertices, less than or equal to 2 edges that are incident on V0 of the color blue, and there are less than or equal to 2 edges of the color magenta, then you will have less than or equal to 4 edges. But you know that the number of edges from each point will be equal to 5. So that gives you a contradiction. So you can always choose 3 edges such that they are of the same color. In this particular example, we have this happens to be the color blue, right? Now check these vertices, these edges, V1, V2, V1, V2, V3, and V3, V1. So if any one of these is of blue color, then what we can say, let's say this particular edge, V2, V3. If this edge was of blue color, then you can choose this triangle, and this triangle will have all edges of the same color. That means V0, V2, V2, V3, and V3, V0 are either all mutual friends or all mutual strangers. So if any one of them are of this blue, are of the same color as these three edges, then you this color. So edge V2, V3 is also of color magenta. Then you can actually form the triangle with these vertices, these edges. So V1, V3, V3, V2, V2, V1. And with these nodes, you will have a triangle such that all their edges are of the same color. Which color is different from the color you have chosen for the vertex V0. But nevertheless, these three have the same color, and hence the three nodes V1, V2, V3 are either all mutual friends or all mutual strangers. I hope it's clear right now. Was your doubt here? Hello, was I able to hear it this time?
Yes, sir.
Okay, okay then the main takeaway is that how you transform the word problem to a graph theoretic problem. Anyway, let's move forward. So this is another well-known theorem uh, that might come across helpful in many competitive programming problems, but this is not that uh, commonly seen. Okay, so in a graph, well, here we assume that E is at least 2. So in a graph with at least two nodes, there are two vertices having the same degree. That is, there exists U and V in capital V such that U not equal to V, but degree of U is equal to degree of V. For example, in this graph, you can see this vertex and this vertex have the same degree, right? Also, this vertex and this vertex have the same degree. Anyway, uh, okay. So, uh, does anyone want to? Does anyone know how to prove this? Okay. Consider any vertex U. Can you tell me the range of degree of? Can degree of U be equal to -1? Can degree of U be equal to n plus 1? No, right?
1 to n minus 1.
Exactly. The degree of a vertex is from 1 to n minus 1. Okay. Now, for the sake of okay, may not. Okay, so you can also have degree 0, right? We do not require the graph to be connected, right? There can be another lone vertex 7 sitting over here, right? So this theorem holds true even for uh, graphs that are not connected. So this makes sense. Okay. Okay. So how many values are there in the range? N
10.
values, right?
And
So let's say for the sake of contradiction, we have a graph, some graph. That's right. Assume there exists GPE such that all degrees are distinct. Now, what does this mean? This means that there will be one vertex of degree 0, there will be one vertex of degree 1, there will be one vertex of degree 2, connected somewhere, there will be one vertex of degree 3, up to the n minus 1, right? Let's say there is no vertex of degree 7.
Like, is degree n minus 1 necessary in a graph?
What do you mean?
Will it like reach the maximum limit for a given node? Means any node?
It can, right? You
No, means
can
I'm
have.
asking if it is necessary. It
What do you mean necessary?
like will it compulsorily reach n minus 1, or it can not reach also?
In this particular, as after this particular assumption, or are you talking about any
In
graph?
general, in general.
In general, so you are trying to prove a statement in general, right? So you must prove, you must have a proof of all possible cases, right? Even if degree n minus 1 is present, even if it's not present. For example, in this graph, degree n minus 1 is not present, right? So n is equal to 7, but you don't have a vertex that has degree 6, correct? But there can be graphs such that degree n minus 1 is reached. So no, it is not compulsory to have degree n minus 1 in all graphs that can be constructed. But when you assume that there is a graph having all degrees distinct, then it is compulsory that n minus 1, uh, there must be a vertex that has degree n minus 1. Does the sentence
Yes,
clear your doubt?
understood.
Okay. So why all of these vertices must be present? I mean, why all of these degrees must be present exactly once as uh, degrees of vertices? Well, let's say if 7 is not present, then you will, the range of degrees will be from 0 to 6, and then 8 to n minus 1. Okay, but there are n minus 1 total values over here, right? That means there will be one particular value of degree that will be repeated for 2 nodes, correct?
Yes.
Clear? Okay. Now, the observation that is, I'm not sure if this is what you're trying to say, but take a look at this node and this node, the node with degree 0 and the node with degree 1. Well, sorry, not degree 1, degree n minus 1. Well, the node with degree n minus 1 connects to all other vertices, right? In particular, the node with degree n minus 1 must also connect the node with degree 0. But that contradicts the fact that this has degree 0. There is an edge that connects this vertex and this vertex, so the degree of this must be at least greater than or equal to 1. Right. So hence there is the entire structure falls apart, and you can argue that there cannot be a graph such that all degrees are distinct. So, is everyone convinced with the proof, or do you want me to clarify this once more? Okay, I hope it's clear. Okay, now let's move on to trees. So the definition of trees was introduced in the last
Actually,
one.
like in graphs, generally, what type of questions they will ask? Only word problems, or anything like
Look, right now, why are we talking about the mathematics of graphs? Well, you won't be directly asked questions that are related to mathematics of graphs, but to understand the algorithms that we'll be covering in the next few classes, you need this foundation of graphs. For example, for division 3, there are problems that uh, require, let's say, connectivity checking using DFS. Then you will be required to check shortest paths using DFS, and so on. So, for example, these handshaking theorem is required to understand the time complexity of DFS, right? Plus, there can be constructive problems that are direct consequences of these mathematical problems.
Okay.
And in general, most of the diff 3 problems are given as word problems, but if you go above a certain rating, then I mean, there is no particular. There is no use of making it a graph, it a word problem rather than phrasing it as a graph problem. I mean, everyone of that rating would be able to identify immediately that okay, there is a graph present inside it. And yeah. So usually, to make the problem statement as simple as possible, they provide the graph theoretic problem statement in the first place. But problems that are, let's say, of the rating 1000 to, let's say, 1300 in code forces, they might have some word problems like this. For example, in CDC series, if you are participated in the last week, there was a problem that had some characters in it, I guess. So yeah, so two characters are related if something happens, and then you can actually you can actually convert the notion of related into this notion of adding edges between these nodes. So yeah, in those problems you can actually reduce the word problems into graphic problems. Was I able to answer your query?
Yes.
Okay. Okay, now moving on to trees. Okay, can anyone quickly tell me the definition of trees? It was covered in the last class. Okay, so basically trees are connected graphs with no cycles. Fine, rings a bell. Okay, I hope uh, everyone remembers the definition of tree by now. Anyway, so there are a couple of examples that this is not a tree and this is a tree because there is this cycle over here and there are no cycles. Okay, let's move on. So now comes another theorem. So basically, this theorem deals with various ways of defining a tree. So this is just one definition of tree, but there are a lot of definitions that are basically equivalent to this definitions that also completely define the tree structure. Okay, so the following definitions are equivalent. Let's look at definitions. Sorry about that. Anyway, following definitions are equivalent. So G is a tree. G is a connected graph with no cycles. So we have defined that these two statements are equivalent. Well, I think you were asked to prove that all trees have E equal to V minus 1 in the last class. Does anyone have a proof? Okay, I think.
Like each node will be connected with one edge, and the last topmost node won't have any uh, edges above it. So it will. down to n minus 1.
I mean, yeah, visually that seems true, but I mean, if you want to make it more
If
rigorous,
you start with two nodes, there'll be one edge between them, and every time you add a node to the tree, you have to add an edge to connect it to the
yeah,
remaining.
yeah, yeah, that is a much better, I mean, much rigorous proof. So you can use induction such that for n equal to 2, or even uh, if n equal to 1, so I'll be denoting size of v by n and size of e by, let's say. So if n equals 1, then m equals 0. So a singleton node is also a tree. This is a connected graph with no cycles as well. And then whenever you increase n by 1, the number of edges also increases by 1. So you can prove this by induction. Yeah, okay. So then this statement is also true if G is a connected graph with number of edges equal to v minus 1. By the way, can anyone prove that this definition is equivalent to this one? I mean, there cannot be a connected graph that has v minus 1 edges but has some cycles in it. Okay, I'll leave this as an exercise for now. Yeah, I mean, try to prove that.
If the graph has a cycle, then the subgraph, which is a cycle, let's say it has n nodes, it would also have n edges. So the remaining graph would not be connected since that would have some number of edges, and
So this has n edges, and then the remaining graph uh, would
let's say
not
the
be
remaining graph has m edges. So then
n
that would need
edges.
m min. No, let's say the remaining graph has m nodes. So then that would have m minus 2 edges. So that can't be connected.
Oh yeah, the remaining graph has if that has, let's call it n prime maybe because we are using m as the number of edges. Then if this particular graph must, this particular subgraph must have uh, n prime minus 2 edges, but then this cannot be connected. Yeah, that completes the proof. Similarly, you can prove the next statement that a graph without it cycles width equal to v minus 1 is also equivalent to this, and this way. This is the these two are very similar proofs. Okay. For the next part, uh, we have, so for given G and given any two vertices U and V, let's say, then there is exactly one path from U to V. I mean, in problem statements, this instead of telling you that uh, you are given a tree, they tell you that you are given a graph, and such that uh, all pairs of nodes in the graph have exactly one path connected. So how do you prove this? Then there are two parts of the proof. One is proving connectedness, and another is proving that there are no cycles. Well, proof connectedness is simple because, well, for any vertex u and v, you have one path. So yeah, that is the definition of connected. Okay. And how do you prove that there are no cycles? Well, you assume that if there is some cycle, then you just take let's say two adjacent nodes in the cycle. The graph may be larger, and you observe that the direct edge from this node to this node is one path, and the rest of the cycle taken in the edges taken in order from, let's say, counterclockwise in this direction is also another path. So you have more than one path if a cycle is introduced in the graph. So yeah, so this proof holds both ways. So if you have two paths from U to V, one in this direction and another in this direction, then you form a cycle. This means that this statement is equivalent to this statement. Okay. Okay, now moving on to the next statement. He is minimally connected. Well, what does minimally connected mean in the first place? Well, minimally connected means that if we remove any edge, it becomes disconnected. So, for example, you see over here that if you remove this edge, 7 will be disconnected from the rest of the graph. If you remove any, if you remove this edge from 1 to 4, these these two will form separate connected components. The point is, if you remove any edge, the entire graph becomes disconnected. Well, to prove this, you can. So again, there are two components to proving this. That there are no cycles and this is connected. So G is minimally connected. So by definition, this is connected. Yeah. So minimally connected means that the graph is initially connected and removing any edge will disconnect it. So the fact that it's initially connected is basically trivially implies that G is connected in the first place. And how do you prove no cycles? Well, again, assume that there is a cycle that is present in the graph. The graph can be larger. Now, if you remove one edge in the cycle, then observe that the graph still remains connected. Why? Because let's say there was a path that used this edge that we removed. Now, what happens if we no longer have the option of traversing this path? Well, we can still move around the cycle and continue with the same path, right? Well, over here there are edges such that you are traversing them twice, but you can just take the symmetric difference of them, I guess. Yeah. So that means if there is a cycle, then this graph cannot be minimally connected. And the proof goes in the opposite direction as well, that if there is, so if the graph is minimally connected, then there cannot be cycles, and if there are cycles, then the graph is not minimally connected. Okay, and the final statement is that G is maximally acyclic. Well, again, let's explain what maximally acyclic means. This means that if we choose U and V such that there is no uh, edge between U and V, so U and V does not belong to E and U not equal to V, then if we connect so initially the graph is acyclic, but if we add one more edge, the graph becomes the graph no longer remains acyclic. Again, the proof of this uh, being equivalent to this is pretty straightforward. We just assume that if there is a cycle. So maximally acyclic means that the graph is already without any cycles. That means the no cycles part is proved. And now you just assume that, well, if this was not connected in the first place, then you can add another edge connecting two separate connected components, and the graph still remains acyclic. So it's not maximally acyclic. Again, So this deduction is proved. Sorry, this deduction is proved. Again, you can maybe prove this deduction just by maybe using this statement as an intermediate point. So you have already proved that this statement is equivalent to this statement. Now you want to prove that this statement implies this statement. Then you can say that, okay, if let's say we are having two nodes U and P, and we want to add this new edge from U to V, but we already know that there is exactly one path from U to V, then adding this new edge would cause the graph to have a cycle with the pre-existing path from U to V. And that's it. So I have talked a lot about this without asking if it's clear or not. So was there any problem in the discussion? Or was everything clear?
Clear.
I hope everything's clear. Anyway, so we have discussed some properties pertaining to degrees of vertices. Then we have discussed some properties of trees. And now we will move on to paths of a graph. Okay, so I've already used the term paths over here. One path connecting them. Now, the definition of paths was also covered in the last class, but just reiterating the same definition. So a path is a sequence of adjacent vertices such that like without repetition. Okay. So this is a path. 4 and 5 are 5 and 4 are adjacent. 4 and 0 are adjacent. 0 and 2 are adjacent. 2 and 3 are adjacent. So the path will be 5. So you can write it as a sequence of nodes 5, 4, 0, 2, 3. But let's write it in this fashion just to make it easier to visualize. So this is a path. Again, this is also a path. 1 to 4. And you can have paths of 0 length as well. So just a singleton node, let's say 6. So 6 in and itself is a path of length 0. So I hope the definitions are clear. Okay. Now, can anyone prove or find a counterexample of the following fact? No edges repeat in a path. Can ever repeat. So in a path, we only talk about without repetition of vertices. Sequence of adjacent vertices without repetition. That means we are talking about repetition of vertices, but can we say that edges are also not repeated, but or you can find a path such that the edge, one particular edge is repeated twice. Anyone?
If an edge is repeated, we will reach to a node which we have already covered.
Exactly. So if you, for example, if you just want to repeat the edge 5 to 4, so you can repeat it in two ways. One way is the second occurrence occurs like 4 to 5. In that case, the node 5 will be occurring twice. So let's say 4 to 5. Now this 4 to 5 can also be just after this. So even if 4 occurs once, 5 will occur twice. And if you are occurring this path 5 to 4 for the second time in this direction itself, then both nodes 5 and nodes 4 occur twice. So that violates the definition. Okay. So yeah, that's a valid. Now moving on to the shortest path problem. So let's talk about weighted graphs right now. So what do you mean by a weighted graph? Well, every edge has some weights assigned to it. And now let's further assume that these weights are non-negative. So in a physical setting, these may correspond to cities and the road distances between them, or maybe the toll tax that you need to pay to traverse from one city to another city using this road. Okay. So for now, let's assume that these weights are non-negative. Now the shortest path problem. So let's talk about the weight of a path or the cost of a path. The cost of a path V1, V2, V3, Vk is basically weights of V1, V2 plus weight of V2, V3 plus so on. Vk minus 1 Vk. So in problem statements, they will ask you the minimum cost that you need to travel from city 4 to city, let's say 0. So how does it look like? So we can have a path from 4 to 2, then 2 to 0. This will be of cost 14, right? Because 7 and 7. Again, you can have a direct path from 4 to 0. This will be of cost 20. Again, you can have a path from 5 to 0. This will have a cost of 12. Again, you can have this path 4 to 1 to 5 to 0. That has a cost of 9. Now the shortest path asks you to find the minimum weight among all these paths. So find the path or just the weight such that the cost of the path from distance u to distance v is minimized. So we write this as, let's say, distance between u comma v is the length of shortest path from u to v. Now what do you mean by from u to v? So the path starts at u and ends at v. Okay. So in our example, we have the shortest path from d the shortest path from 4 to 0 is of length 9 or cost 9. So we synonymously use the words length, weight, and cost of a path for shortest path problems. Okay. Now, one special case of shortest paths is when the graph is undirected and you are asked to find the minimum number of edges. So so the path with the minimum number of edges from U to V. So in that case, you can just assume that all edges have a weight of 1 and then find the shortest path from U. So now the shortest path function. So the shortest path function is basically a function from distance is basically a function from d squared to z or r or n, whatever our field is. But this shortest path function satisfies the properties of being a valid metric. By what a valid metric is, explaining that will take a long time. So I'll just explain the properties that this function holds. So first of all, distance from a node to itself is equal to 0, right? Because you have assumed that all paths are of weight, are of non-negative weight. So distance from 4 to 4 itself is 0. Distance from 6 to 6 itself is 0, because you are having an empty sum, and by convention, the value of an empty sum is assumed to be 0. Okay, so this is property 1. The second property is distance between u and v is equal to distance between v and v. So for this property to hold true, we will be assuming undirected graphs. In directed graphs, this property may not hold, because you can just have one vertex connecting another vertex in one direction and having some weight, let's say 10. So the shortest path from 1 to 2 is of weight 10, but there is no path from 2 to 1. Hence, the shortest path is assumed to have a value of infinity. So those two are not seen. Or you can have a more civilized example like this. So this edge weight is 20, this edge weight is 10. The shortest path from 1 to 2 is 10, the shortest path from 2 to 1 is 20. But in undirected graphs, this is clearly true, right? Because if this has a lower value than this, then you can just follow this path in reverse and get from U to V, which will give you a contradiction, right? The third property is an interesting property. So you can actually observe that the triangle inequality holds true for distance. Right? So what do you mean by triangle inequality? So for three vertices, distance U, V, and W, let's say, distance from U to V plus distance from V to W must be greater than or equal to distance from U to W. So yeah, so I have two questions for you. First of all, why is this called the triangle inequality? And secondly, how do you prove this? So for the first question, why is this called the triangle inequality in the first place? So triangle inequality, you had something like in a Euclidean plane, AB is length of AB is plus AC is greater than BC, right? Can anyone answer this? Okay, over here as well you have vertices. So in the triangle, you have the same setting, right? You have distance from A to B plus distance from B to C is greater than or equal to the distance from A to C, right? But instead of talking about Euclidean distances, we talk about shortest distances in a graph. So that is why we call this a triangle inequality, because this highly resembles the triangle inequality in the Euclidean plane. Secondly, can anyone point out why this is true? So how do you prove statements like this? Well, you assume the contrary. Well, there exists, let's assume there exists u, v, and w such that distance from u to v plus distance from v to w is strictly less than distance from u to w. So we have u, v, so this line in this path have a strictly smaller sum than this path. Now observe that if this is the shortest path from u to w, then instead of going along this path, you can actually go from u to v along this path and then v to w along this path. And the cost or length or weight of that composite path will be the LHS of this thing. But you know that distance of uv is the smallest possible path. So you have a contradiction. So that means that this green path can no longer be my shortest path. The shortest path would rather be from u to v and then from v to w. Does that make sense? Or
Yes.
is it okay? So there's an algorithm called the Dijkstra's algorithm that will be using this particular property multiple times. But let's not dive into that algorithm right now. Okay. Okay, so any function that satisfies these three properties is called a valid metric or a metric space. However, these so distance is a valid metric only for undirected graphs. For directed graphs, this thing fails. This thing still holds true, right? Just check, because this argument does not require you to go back the same path. So for this property to hold true, you must have undirectedness in your. Okay. Okay. Well, now we have understood what shortest paths are. Now let's talk about some other. So everyone remembers what walks are, right? So in walks, you are allowed to uh, have repetition of vertices, right? So you can go from 0 to 4, then 4 to 5, then 5 to 1 again, and then I mean any sequence would stop at some point. That is a valid one. Okay. So now with that definition in mind, we will be talking about something called the Eulerian train. Before that, I'll ask you a general question. So, has anyone seen this kind of a structure before? Or another variant of that structure is this. Anyone, anywhere?
Sort of box.
Okay, so I mean, it's sad that no one in your school gave you this structure and asked you to draw this without lifting your pen from the paper. Uh, that did not happen. Anyone?
Yes.
Okay.
First one.
So, okay, yeah, like there are two versions of this thing. Okay, so let's talk about this particular structure. Well, if you don't include the cheeky ways of folding the paper and all, it turns out that you cannot draw this particular structure uh, with these two conditions. So you cannot lift the pen, and the second property is you cannot repeat edges. So, for example, our nodes over here are these four. I mean, you can call this node to be another node as well, but that does not really matter. Okay. So, formally, what are we asked to do? So, we are asked to find a walk starting at any vertex and ending at any other vertex, such that all the edges are covered at exactly once, right? So, find a walk such that all edges are covered exactly once. Okay. So turns out that this problem is one of the reasons why Leonardo Euler decided to uh, invent graph theory. Let's say. So the problem that he was handling is known as the seven bridges of Konigsberg. So you have some structure like this, and you are asked to walk around starting from anywhere and ending at anywhere. You can use these bridges exactly once, and uh, you have to use all the bridges. Okay. So turns out that neither this problem nor this problem can be solved. Now let's talk about why. First of all, observe that. First of all, let's observe some of the structures that we can draw. By the way, can anyone draw this? Okay, it seems that I got disconnected. What was the last thing that was audible?
The triangular shape.
So whatever I talked about the Königsberg problem was clear, right? So this part was audible, right?
Yes.
So now let's not waste further time. Let's just see if this structure can be drawn or not. So it turns out that this structure can be drawn. So you can start at any point.
Actually, you're not sharing your
Screen is not showing.
Sorry. Okay, thanks for reminding. Is my screen visible right now?
Yes.
Okay. So you can start from this point. You can go over here. Okay, so not from that point. You can start from this point. You can go over here. Okay, let's just put arrows so that it's easier to keep track. Then you go here. Then you go here. Go here. 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 Okay. Now let's have a look at what happens to the degrees of the vertices that we touch. So initially the degrees of all the vertices are all zeros, right? Now when you just start drawing the first line, the degree of this vertex becomes 1. Now when you finish the first line and when you just started drawing the second line, the degree of this vertex increases by 2, and this goes on until you are like about to end. So for this you add 2 to this, then you go here, you have reached this point, you come down, you add 2. Now you come down here, you go over here, you add another 2. You come over here, you go upwards, so you add 2 over here, you touch this point, and you're about to end, so you add 2. But in the last edge that you draw, you add only 1, right? Now what does this mean? Except for the starting and the ending vertex vertices, you will be only adding 2 to all the degrees of other vertices. So this means that the number of odd vertices that we have must be less than or equal to 2. Okay, too many interruptions. Anyway, so the point is we cannot have more than 2 odd vertices, because if there is a third vertex having an odd degree, you cannot start from one point and then go in, go out, go in, go out, go in, go out, and then reach the end point. That will just make the degree of this vertex even. Now, if you check this diagram, you have degree equal to 3 over here, degree equal to 3 over here, degree equal to 3 over here, degree equal to 3 over here. So you can never complete this diagram by just using these rules. Does that make sense?
Yes.
Also, my screen is visible, right? Screen visible, audible.
Yeah.
Okay. Okay. And the same thing happens in here as well. So that you can actually formulate this as a graph like this. There can be multi-edges. That's not a problem. And you'll observe that the degree of this vertex, this vertex, this vertex, as well as this vertex, all are odd. So since you can only afford at most two odd vertices, you cannot have uh, a path that covers a walk that covers all edges exactly once. So in particular, a walk that covers all edges exactly once is called an Eulerian tree. Anyway, uh, so we are towards the end of today's discussion. Now there is another uh, property that for all. Okay, so for example, what happens if the number of odd vertices is zero? Can you draw it? Well, in that case, you can just start. You'll just have to start and end at the same point, right? For example, if it is just a cycle, so you can start and end at the same point. So this plus one and the ending plus one will be on the same vertex, and that will give you an even degree for all vertices. Okay. What happens if there is exactly one vertex which is having an odd degree? Anyone?
Is it possible?
Sorry.
In only one vertex having or degree is not possible.
Exactly. Because we had a corollary that the number of vertices that have odd degree has to be even. So it has to be either 0 or 2 or 4 and so on. Right. Okay. Now you can try to prove it in the other direction as well. So for all graphs that have one vertex, that have two vertices uh, having odd degrees and all other even degrees, you can actually draw them for all such graphs, right? We have proved the opposite, that if the number of degrees have, if the number of nodes that have an odd degree are greater than 2, then it's not possible at all. But it can still be the case that there are some graphs that have two odd vertices and all even vertices, but it's still not possible to draw them. Just try and prove that it's actually the case that you can draw all of them using these tools. Okay, so I guess we are at the end of today's discussion. So, uh, is there any question?
Actually, you're muted.
Oh, okay. I wanted to stop. I wasn't muted when I made this claim, right? Was I muted when I said
No,
you do
no.
this? No, right?
Mm.
Thank God. Anyway, I wanted to stop sharing my screen. Anyway, let's keep the sharing on. So, any discussion, any questions regarding today's class or previous classes, or any suggestions, comments? Okay, I hope I'm audible this time, but yeah. Okay, I'll assume that there are no questions but in today's class. I'll upload these stripes in the file section and okay. So there are no questions from today's discussion or any other previous discussions, right? Okay, then I think we can call it a day then. Moina, do you have any other uh, announcements?
No, I don't. Class.
Uh, are you
Next class is on Saturday or Sunday?
I mean, if this is the case of the attendance, I mean, I'm doubtful that the next class will be held in the first place.
Yeah.
But I think it will be on Sunday because the Saturdays are.
Yeah, on Sunday we have a test on electricals. Morning we have.
Oh, okay.
So I
Okay.
think Saturday most of the people won't come.
Oh, okay. Okay, I mean, if so, NSEMs end at 24th June,
Yes.
right?
Yes.
Okay, so maybe let's see if we have a class in the next week, this Saturday or Sunday at all, or uh, let's pause it till 24th. Okay, we will let you know. Okay. Okay then. Bye. Yes.
Yeah. Oh wait, this is being recorded.